My name is Wyatt Vick, and I'm a senior at St. Teresa High School.
My name is Charlie Klein. I'm a senior at St. Teresa High School, and our project this year is harvesting electricity from piezoelectric crystals.
So the problem here that we're trying to address is essentially the use of fossil fuels or producing energy that creates greenhouse gases. Many countries and corporations have set goals to limit the amount of greenhouse gases that they produce, and one possible way to achieve this would be to find alternative means of producing electricity. An alternative method of producing electricity that produces no greenhouse gases or carbon for the atmosphere would be beneficial to people all over the world and many corporations and countries as they reach for their carbon net zero goals.
Piezoelectricity was discovered by Jacques and Pierre Curie in the late 1800s, and nowadays it is used in lots of objects that you encounter in your day-to-day life, such as your phone, speakers, microphones, and even watches.
So piezoelectricity is the electrical polarization of a material in response to mechanical stress. Piezoelectric materials are primarily crystals. There's also ceramics, and there's new research in piezoelectric polymers and whatnot. However, the first materials were crystals, and piezoelectric crystals have asymmetry in each of their crystal cells. What this does is when the crystal is just sitting there, it is electrically neutral. However, when mechanical stress is subjected to the crystal, essentially the average location of the positive charges and the negative charges, those will move to different locations. Due to this, there will be a flood of negative charge to one side of the crystal and positive to the other. If the pathway is given for this charge to move on, then it can be used to do work.
In order for our device to be successful, it had to first meet some design parameters. It had to be at least 5% efficient. It had to weigh less than 100 grams. It had to cost us less than $5 to make. It had to be able to charge a capacitor to at least 1 volt, and it had to be able to light an LED.
So we had a couple preliminary designs, and we chose two different piezoelectric materials based on their properties for our preliminary designs. The two materials were sodium potassium tartrate, or Rochelle salt, and lead zirconate titanate, or PZT. So we chose sodium potassium tartrate because it has some of the highest piezoelectric coefficients out there. It's also extremely cheap and uses very safe materials, essentially food grade materials, and we believe that it would have some potential in producing usable electricity.
We decided to use the PZT crystals or PZT ceramics because they are very widely used currently, such that they're used in barbecue lighters. So the longer lighters are piezoelectric lighters. We decided that we would use these crystals. We would use these crystals that are used in the lighters to harvest our electricity from a piezoelectric unit. This would be the unit that we collect from a lighter.
So the materials that we used to actually create our prototypes were potassium bitartrate, sodium bicarbonate, water, a stove, glass measuring cups, plastic containers, filter paper, a metal pot, and measuring spoons. That was for the Rochelle salt prototype. For the PZT, or the lead zirconate titanate device, we used several piezoelectric lighters, a metal case, silicone caulk, and alligator clips. As for the electronics that we needed to actually store the electricity produced by these crystals, we needed a breadboard, two capacitors, 4 diodes, several jumper cables, some aluminum foil, and then we needed a voltmeter and a resistor as well to complete testing. So to produce the sodium potassium tartrate, we did this ourselves. We needed to combine potassium bitartrate, or cream of tartar, with sodium carbonate, which we made from sodium bicarbonate in the stove. We combine these in boiling. We add the sodium carbonate in small increments until eventually the solution goes clear. We then remove that from heat, filter it through filter paper, and put it into a fridge for about 4 days. When it gets cooler, it's super saturated solution, so it crystallizes, and after about 4 days, we take it out, remove the crystals, dry them immediately so that no crystals form on the surface, and that's how we made the Rochelle salt.
So in order to get our piezoelectric units from the PZT, we had to first buy barbecue lighters. We would then take these lighters apart and harvest this unit, which has a small plastic button and a small plastic case. As well as inside of the case, there is a small spring, a very stiff spring, and a little tiny hammer that would hit on this piezoelectric ceramic, sending an energy blast through to this, as well as through this. We would take these wires and connect them into one point, and then connect a wire to the bottom here, which would allow us to connect them to our breadboard.
So for the electronics, what we had to do was create a bridge rectifier. This is due to the fact that piezoelectric materials produce electricity as AC current. In response to an impact, there will be a large spike in voltage, either positive or negative, and then one in the opposite direction, depending on the orientation of the crystal. We took some oscilloscope readings, and we would see upon impact, one large spike up, followed by a large spike down, and some other kind of noise following that. So you can see here, there is the bridge rectifier, which used for diodes. We have two capacitors that store the electricity. These capacitors and the capacitors came from an old laptop charger and an LED light bulb, so they were rated for fairly high voltages, about 200 to 400 volts. And yeah, this was the electronics that we plugged our device into.
So for our testing, we were not able to test our brush shell salt as it could not charge our capacitors to a high enough voltage. This, however, was not the case for our PZT units. Our PZT units were able to charge our capacitors to a high enough voltage to test. So in order to test these, we would first get 4 of these units and put them into a small frame made out of Mechano metal pieces. We would bolt it together with machine screws, and then in order to perform our testing, we would take these 4 units and press them 50 times, recording the voltage after every 5 presses. We would, after pressing 50 times, we would then discharge using a resistor, and then we would start over. We did this for 6 trials.
So one important thing, this is a new iteration that we made after testing that was a 3D printed case as opposed to the metal case.
So when looking at our quad board, you can see our graph titled average voltage versus number of impacts. As you can see, as the number of impacts increases, our voltage also increases. It does this in a linear relationship.
So from the average voltage in the capacitor, we were able to calculate the average energy in the capacitor using the equation energy in a capacitor equals 1/2 times capacitance times voltage squared. You can see here that the energy also increases with the number of impacts. However, it does not appear to have a linear relationship. We did calculate confidence intervals with alpha equals 0.05, and that did support within those intervals that the relationship was increase in voltage and increase in energy with increase in number of impacts. But it is important to note that the average energy did not appear to be linear and actually appeared to have a more quadratic relationship. Additionally, we analyzed that data further and calculated the change in energy per 5 impact interval. And you can see here that this graph looks approximately like what one might expect the derivative of the average energy versus number of impacts graph to look like, as it is the change in energy over number of impacts. You can see here that for each interval of 5 impacts, the energy change actually got larger on average.
So in conclusion, we were not able to test our Rochelle salt, so therefore it did fail all of our design parameters. However, it did not fail the design parameter of cost. It would have been a very, very cheap piezoelectric crystal to try to harvest electricity from if it could have charged our capacitors. That is not the case for our PZT units. Our PZT units were able to pass all of our design parameters except for efficiency. Our units had a 0.042% efficiency.
So as far as some of the discrepancies or the unexpected results, we can see that when performing the same procedure, which would be the 5 impacts over and over again up till 50, one would expect that the energy increase would be constant. However, we did not observe this. We observed a constant increase in voltage. And as we know, energy is voltage squared. And a constant increase in voltage is not a constant increase in energy. One would not, it's very unexpected that the energy, because essentially what we observed was energy increasing in larger and larger quantities for the same process. So we believe that the reason this happened was due to limitations posed by our electronics. The capacitors were rated for about 200 to 400 volts. However, the PZT, which we tested using a voltmeter and an oscilloscope, was capable of producing voltages over 600 volts. And we believe that due to the fact that these electronics may not have handled those high voltages well, it was only allowing a constant voltage through and essentially limiting the amount of energy that made it through each time, which produced the relationship that we saw. We think that over a larger amount of impacts, it's possible that new relationships might have been revealed. But essentially, overall, we concluded that the lead zirconate titanate sample device could likely be used to power several different low power applications. However, we do not believe that it will make a significant impact in the global energy usage, basically just due to its low efficiency and the low amount of energy that it was actually able to put out.
We believe that there are a wide range of uses for our piezoelectric units. We believe that first they could be inserted into roads such as in intersections or before an intersection where a stop sign that would flash or a stoplight would be. Whenever a car would drive over these units, they would send a small charge to these stoplights or stop signs, allowing them to charge a power bank and flash throughout the day or night. We also believe that in train tracks, these would be very useful because a train is a large object with lots of wheels. So every time that these wheels on the train would roll over our piezoelectric units, it would charge a small power bank again, which could be used to power either the lights that warn drivers of a train crossing or even the gates. We also had the idea to put piezoelectric units inside of a wall, which would be spring loaded, and then whenever a wave would crash into this wall, these would be on the near the ocean. So whenever a wave would crash into this wall, it would spring back and push into our piezoelectric energy harvesters, and this would send a small charge again, able to power a power bank, which would then be able to during the night light any lights across the boardwalk.
So we thought of some other potential applications that could be used for a slightly modified version of our device. These would use a device that produces smaller amounts of electricity with much smaller forces applied, potentially even opening the door for Rochelle cell to be used, which obviously was not strong enough to undergo testing with our actual device and did not produce high enough voltages. However, it does open up the door for further study in this. Would be using a piezoelectric generator in tracking tags used in studies on animals. When it comes to larger animals, the tags can be much heavier and can include their own batteries because the larger animal doesn't notice the weight. However, when it comes to smaller animals, it gets harder and harder to make tags that have their own energy sources because either the battery is too heavy for the animal or the battery is small and has a very short life. Um, Tags that have their own energy source can be much more precise than those without. And if a tag were to use a piezoelectric generator instead of a battery, it could be charged over time by small movements the animal makes, and eventually, and every now and then, once the capacitor charges, set out a ping, which would provide a very precise location for scientists to find the animal. Additionally, a similar type of device could be added to many different implants used in humans. It could potentially be used to extend the battery life of things like pacemakers or insulin pumps. And for slightly less vital implants, it could power them completely, such as certain implants that measure blood chemistry or other types of applications. Additionally, another more personal application for us as runners is in running. There has been a recent attention to blood lactate levels during training, and this is used by this is a sensor that detects the lactate in the blood of runners. So a device could be made to detect the lactate levels, and it could be made to be powered by a piezoelectric generator. When someone is running or going through a hard workout, there's a bunch of guaranteed movement right there. And this could be used to reliably power the device and give the runner a good approximation of what their blood lactate level is throughout training. Thank you.
Thank you.